So in this lesson, I'm going to be teaching you guys about intermolecular forces. Those are the forces between molecules. We've talked about briefly intramolecular forces, which are the forces, the attractive forces within a molecule. Specifically, we have ionic, covalent, and metallic bonding. But in order to talk about intermolecular forces, the forces between molecules, I need to review the concept of polar and nonpolar molecules. So to get started, the atom that is more electronegative in a covalent bond, it is going to hog the electrons, and as a result, we say that it has a partially negative charge because it has a higher electron density around it. So it's partially negative, not completely negative because it hasn't stolen the electrons, but it's hogging the electrons towards it because it has a greater attractive force for those electrons. Now, if you have a less electronegative atom, the atom that's less electronegative, it's going to have a partially positive charge. And so there's going to be a separation of charges, a partial positive and a partial negative. And that separation of charges is called the dipole, and we represent it as an arrow. So as you can see here, fluorine is more electronegative than hydrogen is. So fluorine has a partial negative charge while hydrogen has a partial positive charge. So we represent that dipole with an arrow, as you can see on the right-hand side. Now, in determining if a molecule is polar or nonpolar, if the dipoles do not cancel out, then the molecule itself is going to be polar. So hydrogen and fluorine, that hydrofluoric acid right there, is going to be polar because, as you can see, that arrow, that dipole, is not canceled out. If the dipoles do cancel out, then the molecule is going to be nonpolar. So let's look at an example in which the dipoles do cancel out. Let's look at carbon dioxide. Now, if you draw the Lewis structure for carbon dioxide, it's going to have two double bonds, and therefore it is going to be a linear structure. Now, because oxygen is more electronegative, both oxygens there are going to have a partial negative charge, and so the arrows are going to point towards the more electronegative atoms, so they're going to be pointing towards oxygen. Now, if you look at that, since you have an arrow going to the left and an arrow going to the right, those dipoles actually cancel each other out, and as a result, the molecule itself is going to be nonpolar. So being able to identify molecules as polar or nonpolar is key when we're determining the type of intermolecular forces. And there are 4 different types of intermolecular forces that we're going to very quickly look at. The first one is London dispersion forces, also just called dispersion forces. Now, London dispersion forces exist in every single molecule or atom that exists on Earth. There is always a slight attraction between atoms or molecules, even if we decide to ignore them like we did with our gas laws. So how exactly is that attractive force created? Well, if you look at this example, this is helium. If you have atom A and atom B, the electrons, which are shown on the top left and all of the top drawings right there, those electrons can be anywhere at any one instance. So if you look at the center diagrams, the one on the bottom, notice that the electrons happen to be lining up on the left-hand side of atom B. And since they are lining up on the left-hand side of atom B, because they can honestly be wherever, but they just happen to line up there, then the right-hand side of atom B is going to be partially positively charged. Well, since it's partially positively charged, that's going to have an effect on atom A, as you can see in the C diagrams. The partial negative is going to repel the electrons in atom A, causing the left-hand side of atom A also to be partially negatively charged, while the right-hand side of atom A will be partially positively charged. And so that separation of charges, even though it's a slight difference in charges, that's going to cause an attraction. That attraction is called London dispersion forces, and so it exists in every single type of molecule, in every single type of atom. So while I'm going to be talking about 3 more types of intermolecular forces, all of these also have London dispersion forces. Now, London dispersion forces, when we're trying to list out all of the different types of intermolecular forces that molecules or atoms can have, if you have a nonpolar molecule, the only intermolecular force it will have is London dispersion forces. Now, the other ones, or the other types of intermolecular forces I'm going to talk about, happen to be for polar molecules. So let's talk really briefly about how the strength of London dispersion forces can vary. And the term that I have to use in order to talk about that is polarizability. Now, polarizability is the ease with which the charge distribution is distorted. And so when we're comparing the strength of different London dispersion forces, we're going to be using this term polarizability, or how polarizable a molecule is. Now, as you can see from this chart right here, neon has a weaker intermolecular force, has a weaker London dispersion force than fluorine does. Argon has weaker than chlorine, krypton than bromine, xenon, and iodine. Now, we know that because if you look, and I'm going to be talking about this in the next lesson, but that's because their boiling points are higher, which means they're holding on to one another much more tightly, which means that their intermolecular forces are stronger. So, why are fluorine, chlorine, bromine, and iodine, why do they have such a stronger intermolecular force, such a stronger London dispersion force? Well, that's because they are more polarizable. If you notice, all of those molecules have a larger mass than those noble gases that they're compared to. And so a molecule or an atom is more polarizable. It's easier to distort the charge and create this London dispersion force if they have more electrons, and they have more electrons with larger masses. So when you're comparing the strengths of London dispersion forces, the more massive a molecule is or an atom is, the greater its mass, the more electrons it has, and therefore the more polarizable it is. The other factor that influences the strength of London dispersion forces is the molecular shape. If you compare N-pentane versus neopentane, notice that N-pentane has a linear structure while the other one is spherical. So notice that N-pentane, because it has a higher boiling point, that means it has a stronger London dispersion force. And this is because there's a larger surface area in which those two molecules can interact with one another. So not only the more massive, but also the more surface area a molecule has, the stronger the London dispersion forces. Molecular shape can be hard to determine without drawing it out. So the easiest one to determine is to compare mass. However, if you're given the shapes of two molecules and asked to compare, just identify which has a larger surface area, and that will be the one that has stronger London dispersion forces. The next type of intermolecular force is dipole-dipole forces. Now, dipole-dipole forces only occur between polar molecules, and that's because those polar molecules have a permanent dipole. And so dipole-dipole forces are those attractions between dipoles, the partial positive and the partial negative, that we saw in London dispersion forces, but it's permanent. And so as a result, it causes molecules to be even more attracted to one another. So molecules that are polar, they will have London dispersion forces, but dipole-dipole forces as well, which puts them over the edge, which means that they have an even stronger attraction between one another than nonpolar molecules. And the strength of dipole-dipole forces increases as you increase the polarity of the molecule. And you get to the point at which the difference in polarity is so great that you no longer have dipole-dipole forces. You instead have the third type of intermolecular force, which is hydrogen bonding. So if you look at this right here, in order to have hydrogen bonding, you need a hydrogen that is bound to either an oxygen, a nitrogen, or a fluorine, as you can see here, and then it's going to be attracted to another oxygen, fluorine, or nitrogen. And the reason why hydrogen bonding is so much stronger than London dispersion forces and dipole-dipole forces is because there is a great difference in electronegativity between oxygen and hydrogen. And so as a result, hydrogen there is going to be very partially positively charged, and the oxygen, fluorine, and nitrogen are going to be very partially negatively charged. And so that attraction is going to be even greater than it was in dipole-dipole because of the great difference in polarity. So that's the third type of intermolecular force. Remember, for hydrogen bonding, you need fluorine, oxygen, or nitrogen. It is fun. Hydrogen bonding is fun, but those hydrogens need to be bound to an oxygen, fluorine, or a nitrogen as well. The fourth type of intermolecular force is ion dipole forces, and these result from the attractive forces between a polar molecule, so for example water, as you can see, and then ions. So as you can see with the chloride ion, it is attracted to the partially positively charged section of water. And for sodium, it is attracted to the partially negatively charged section of water. And so these are extremely strong because these attractive forces are extremely strong because chlorine and sodium have complete charges instead of just being partially negatively or partially positively charged. And so these ion dipole forces exist whenever you dissolve an ionic compound in water. So let's actually compare intermolecular forces. These are some rules to go by. So if you have two molecules that have comparable molecular weights and shapes, one is way heavier than the other one, the dispersion forces are going to be about the same. And so where you look now is to compare. And so to compare the intermolecular forces, it's not going to be because of London dispersion forces. Instead, you need to compare and look at the differences in the strengths of their dipole-dipole attraction. So that can be dipole-dipole forces or hydrogen bonding. Now, the intermolecular forces get stronger as molecular polarity increases, as we said, and therefore molecules that have hydrogen bonding are going to have the strongest interactions. So assuming that molecules have about the same molecular weight and shape, what's going to dictate the strength of the intermolecular force is going to be if there's dipole-dipole interactions. And then if there are dipole-dipole interactions, if those happen to be hydrogen bonding, remember you have to have hydrogen, F, O, or N, and the molecule has to be polar, then hydrogen bonding is what is going to dominate and cause the intermolecular forces to be the strongest. Now, when you have molecules that have very different molecular weights, dispersion forces are actually going to dominate. And so the molecule that has a higher molecular weight is going to be the one with the stronger attraction.